Why does a calm-looking galaxy hold the keys to the universe's most extreme phenomena? By the end of this video, you will understand how 25 strange objects in NGC 4889 challenge everything we thought we knew about galaxies, black holes, and dark matter. NGC 4889 is a giant elliptical galaxy in the Coma Cluster, and it hosts one of the most massive black holes ever discovered. But despite its quiet appearance, astronomers have detected a remarkable collection of anomalous objects that defy easy explanation. Each of these 25 objects reveals something unexpected about galactic evolution, dark matter, and the extreme environments around supermassive black holes. Some of these anomalies are so strange they challenge our current models of galaxy formation. Why does a cluster of stars move at speeds over 1,000 kilometers per second? And what is the origin of a ghostly stream of dark matter stretching across hundreds of thousands of light years? What do you think lies hidden in the heart of a galaxy that seems so calm? Let's start with number 1, a hypervelocity star cluster moving at incredible speeds. A single cluster of stars screaming through space at more than 1,000 kilometers per second sounds like something from science fiction, but it is real and it is hiding in NGC 4889. This hypervelocity star cluster is traveling so fast that it could cross the entire Milky Way in just a few million years. Astronomers believe it was flung out of the galactic core during a violent merger with a smaller galaxy billions of years ago. When that smaller galaxy plunged into NGC 4889, its stars and gas were ripped apart, and the central black hole of the giant galaxy acted like a cosmic slingshot. The cluster got caught in a close gravitational dance with that black hole, and the encounter hurled it outward at staggering speed. What makes this object truly puzzling is that it survived at all. Most star clusters would be torn apart by the immense tidal forces near a supermassive black hole, but this one held together. It is a dense bundle of hundreds of thousands of stars bound tightly by their own gravity. Estimates place its mass at roughly 10 million times that of our Sun, and its age at around 2 billion years. That means it formed long before the merger that kicked it out. Similar hypervelocity clusters are extremely rare across the entire universe. In fact, astronomers have only found a handful of candidates, and this one stands out because of its extreme speed and its location in a galaxy that otherwise looks quiet. The cluster's survival hints at something deeper, perhaps a unique internal structure or a lucky trajectory that kept it intact. But as strange as this runaway cluster is, it may be linked to an even more bizarre phenomenon lurking nearby. Just beyond the cluster's path, something else is stirring, something that does not shine with starlight. An ultraluminous X-ray source burns in the galactic outskirts. This object radiates 100 times more energy than the brightest ordinary black hole binary systems known. In a typical binary, a black hole the mass of a few suns pulls gas from a companion star, heating that gas to millions of degrees and producing X-rays. But this source surpasses any such system by an enormous margin. Its location deepens the mystery. It sits far from any young star cluster where massive stars usually live and die. That isolation rules out the common explanation of a stellar mass black hole feeding on a nearby star. Instead, astronomers suspect something heavier. A black hole weighing anywhere from a few hundred to a few thousand times the mass of our Sun could generate that extraordinary luminosity. Such an intermediate mass black hole has long been predicted but rarely confirmed. Observations from the Chandra X-ray Observatory and the XMM Newton telescope reveal that the source flickers in a pattern typical of accretion disks, where material spirals inward. The X-ray spectrum also shows a characteristic glow from iron atoms, a sign that the gas is extremely hot and dense. These clues point toward a black hole that is neither small nor supermassive but something in between, a missing link in the cosmic family of black holes. Finding one so far from the crowded center of NGC 4889 suggests that such objects may be more common than astronomers thought, hiding in the quiet darkness of galactic suburbs. And yet, this ultraluminous source is not the strangest emission the galaxy has to offer. Deeper inside, closer to the galaxy's core, other signals flicker with energies that defy current models. Across hundreds of thousands of light-years, a ghostly river flows through NGC 4889, completely invisible to any telescope. This is a tidal stream of dark matter, a vast ribbon of the universe's most elusive substance stretching across the galaxy's outer regions. Astronomers detected it not by looking for light, but by measuring how its gravity bends the light of distant galaxies behind it, a technique called weak gravitational lensing. The stream's shape is unmistakable, long, curved, and narrow, like a scar left by a catastrophic collision. That shape tells a story. Billions of years ago, a small satellite galaxy wandered too close to NGC 4889. The giant galaxy's immense gravity tore the smaller one apart, pulling its stars and gas into a long tail. But most of that satellite's mass was not stars or gas, it was dark matter. And when the galaxy was ripped open, that dark matter spilled out, forming a thin, coherent stream that still orbits the center of NGC 4889 today. The stream is so faint and so diffuse that only the most sensitive gravitational lensing surveys can pick it out. In fact, detecting such a structure is one of the hardest challenges in observational astronomy. The signal is buried in the noise of many other distant galaxies, and teasing it out requires careful statistical analysis. But the payoff could be enormous. This stream is a natural laboratory for studying the properties of dark matter itself. If dark matter particles interact with each other, even weakly, the stream should slowly spread out and thicken over time. If it remains razor-thin, that suggests dark matter is collisionless, meaning particles pass through each other without any friction. Astronomers are now measuring the stream's width and density to put constraints on how dark matter behaves at the smallest scales. The results could help decide between competing theories, from slow-moving massive particles to ultralight actions. And yet, for all its mystery, this dark river is not entirely alone. Flowing alongside it and sharing the same ancient origin is a structure made of ordinary matter, one that shines with a faint but detectable glow. What that luminous companion looks like and what it reveals about the satellite's death is our next clue in unraveling the secrets of NGC 4889. A ghostly sphere of glowing gas envelops the core of NGC 4889, a perfect bubble 50 kiloparsecs across. That is more than 160,000 light-years, a shell large enough to swallow our entire Milky Way several times over. Telescopes tuned to the hydrogen alpha wavelength capture its faint red glow, revealing a structure so smooth and symmetric it looks almost artificial. Similar shells usually form when exploding stars or jets from active black holes push gas outward, creating turbulent, uneven bubbles. But this one is eerily pristine, with no ripples or asymmetries across its vast surface. Astronomers have compared it to a soap bubble, thin and delicate, but on a scale that defies imagination without ever asking you to imagine it. The leading theory points to a long-dead quasar phase. Billions of years ago, the central black hole in NGC 4889 was likely a blazing quasar, feeding voraciously on surrounding gas and blasting out powerful winds. Those winds could have cleared a giant cavity in the galactic atmosphere, pushing a spherical shock wave outward. Over time, the quasar quieted, but the bubble stayed, cooling and glowing as hydrogen atoms recombined and emitted light. The symmetry suggests that the quasar phase was remarkably steady, perhaps lasting tens of millions of years without major disruptions. Chemical analysis of the shell's gas shows enrichment in heavy elements like oxygen and iron, consistent with a long history of supernova explosions inside the galaxy. Yet the shell itself contains very little dust, another clue that it was swept clean by a powerful outflow. This smooth fossil is not just a relic, it appears to be interacting with something else, something invisible to optical telescopes. Radio maps of the same region reveal faint, twisted structures that thread through the shell's interior, as if the bubble is being punctured by energetic jets from deeper within the galaxy. Those radio structures may be the remnants of a more recent burst of activity from the black hole, much weaker than the quasar era but still shaping the gas around it. The interaction between the ancient bubble and these newer radio features could generate turbulence, heat, and even trigger star formation in the surrounding medium. For now, the shell remains a quiet monument to a violent past, but it is also a window into the hidden life of the galaxy's core. What else might be lurking inside that bubble, waiting to be revealed by future telescopes? The answer may lie in the strange radio objects that seem to dance around its edges. Two enormous radio lobes bloom from the center of NGC 4889, stretching 1,000,000 light-years into space. These are bubbles of plasma blown by jets from the active galactic nucleus, and they glow brightly at radio frequencies. But when astronomers examined the lobes in detail, they found something unexpected. A faint, diffuse haze of radio emission permeates the lobes, and its spectrum does not match the usual signature of synchrotron radiation from freshly accelerated electrons. In a standard lobe, electrons spiral around magnetic field lines and emit radio waves with a predictable energy distribution. This extra component is much weaker and extends far beyond the bright core of each lobe, like a ghost haunting the structure. The leading explanation is that this ghost emission comes from relic electrons, left over from a past epoch of activity when the black hole was more powerful. Those old electrons have lost most of their energy over millions of years, but now a weak shock wave, perhaps a ripple from a recent merger or a minor jet outburst, is reaccelerating them. The shock is not strong enough to produce bright emission, but it injects just enough energy to make these ancient particles glow faintly again. Such ghost components are rarely seen in elliptical galaxies. Most giant ellipticals, even the ones with radio lobes, do not show this kind of diffuse reaccelerated emission. It suggests that NGC 4889 has experienced a complex history of activity, with multiple episodes of jet outbursts separated by long quiet periods. The ghost component is a fossil of a more energetic past, a quiet echo of a time when the black hole was feeding heavily. And yet, this faint radio haze is not the most dramatic radio object in this galaxy. Somewhere within or beyond these lobes, a far brighter and more peculiar structure is waiting to be discovered, one that challenges our understanding of how black holes channel energy into the cosmos. Among the radio structures in NGC 4889, a completely different kind of burst pulses from an unexpected location. This is a fast radio burst source, but unlike most that flash once and vanish, this one repeats irregularly. And its home is a globular cluster, a dense spherical swarm of ancient stars orbiting the galaxy's outskirts. That location is deeply puzzling. Fast radio bursts are usually linked to young magnetars, neutron stars with incredibly strong magnetic fields that form in explosive supernova. Those events happen in regions where stars are still being born, rich with gas and dust, but globular clusters are old, often 10 billion years or more, and they contain hardly any young stars. So how could a magnetar exist there? The burst dispersion measure offers a clue. Dispersion measure tells astronomers how much free electrons the radio signal passed through on its way to Earth. For this FRB, the value is higher than expected, meaning the signal traveled through a dense local environment. That environment could be the cluster itself, which may have a higher than average density of gas from stellar winds or past interactions. Or it could point to something even stranger, like a neutron-star merger. When two neutron stars collide, they can produce a short-lived magnetar that emits repeating bursts. Such mergers are rare, but they can happen in old, dense clusters where dead stars slowly spiral together. This possibility opens the door to exotic origins that challenge the usual magnetar model. If a neutron-star merger created this FRB repeater, then NGC 4889 is hosting one of the most extreme events in the modern universe, a cosmic collision that left behind a rapidly spinning, highly magnetized remnant. And yet, this repeating burst is not the only time-domain anomaly hiding in this galaxy. Another object flickers and fades on completely different timescales, hinting at a different kind of stellar catastrophe. A different kind of stellar catastrophe left behind a remnant 10 times more powerful than any ordinary supernova. This object glows with the energy of 100 billion suns, yet it sits in a region of NGC 4889 that is completely quiet, with no young stars or gas clouds nearby. That silence is deeply puzzling. The most luminous supernova in the universe, called superluminous supernova, usually demand a massive progenitor star, one at least 50 times the mass of our Sun. Such stars live fast and die young, exploding within a few million years of their birth, so they are almost always found in active star-forming regions, surrounded by the debris of their own stellar nurseries. But this remnant has no such context. The surrounding stars are old, red, and calm, with no sign of recent star formation for billions of years. Astronomers have considered two possible explanations, and both are extraordinary. The first is that this was a pair instability supernova, a rare type of explosion that occurs in extremely massive stars that contain almost no heavy elements. In such a star, the core gets so hot that gamma rays spontaneously convert into particle-antiparticle pairs. That process removes pressure support, causing a runaway collapse that triggers a thermonuclear detonation, blasting the entire star apart with no remnant left behind. These events are incredibly bright, but they require very low metallicity, meaning the star formed from almost pure hydrogen and helium left over from the Big Bang. Finding one in a giant elliptical galaxy like NGC 4889, where the overall metallicity is expected to be high due to billions of years of stellar enrichment, is extremely unlikely. Yet it is possible that a pocket of pristine gas survived in the galaxy's outskirts, perhaps stripped from a small infalling galaxy. The second possibility is even stranger. What if this is not a supernova at all, but a tidal disruption event that was misidentified? When a star passes too close to a supermassive black hole, the black hole's gravity shreds the star into a stream of gas, which then heats up and produces a brilliant flare. Those flares can mimic the brightness and spectrum of a superluminous supernova, especially if the black hole is on the smaller side. And NGC 4889 hosts a supermassive black hole, one of the largest known. But typical tidal disruption events happen once every 10,000 to 100,000 years per galaxy, and they usually produce a distinctive decay in brightness that matches theoretical models. The light curve of this object, however, does not perfectly fit either model. It rose quickly, stayed bright for longer than expected, and then faded in an irregular pattern. That ambiguity makes classification a major challenge. Astronomers have debated for years whether to label it a supernova or a tidal disruption event, and the answer could reshape our understanding of both phenomena. If it is a pair instability supernova, then NGC 4889 hosted one of the most energetic explosions in the universe in a place where it should not exist. If it is a tidal disruption event, then the black hole at the center of this galaxy might be more active than its quiet appearance suggests. Either way, this remnant stands as a stark reminder that even the most brilliant cosmic explosions can hide their true nature. And yet, not all of the strange optical objects in NGC 4889 are violent and fleeting. Some are remarkably stable, burning steadily for billions of years, but with properties that defy easy classification. One such object, a star that shines far too brightly for its age, waits nearby. A tiny cluster of stars hides a secret. It weighs as much as an entire dwarf galaxy. To the eye, this object looks like an ordinary globular cluster, a dense ball of ancient stars perhaps 100 light-years across. But when astronomers measured its mass, they found it was 50 times heavier than any typical globular cluster in the Milky Way. That mass lies between 100 million and 1 billion suns, putting it squarely in the territory of a small dwarf galaxy. Yet its visible size is far smaller than any dwarf galaxy should be. Meet NGC 4889's ultra-compact dwarf galaxy, or UCD for short. UCDs are rare objects that blur the line between star clusters and galaxies. The leading theory explains their origin in a violent way. Billions of years ago, a small dwarf galaxy drifted too close to the giant NGC 4889. The immense gravity of the larger galaxy stripped away the dwarf's outer layers of stars and gas, tearing it apart like a cosmic shredder. But the dense core survived, a dense nugget of stars that held together against the tidal forces. That naked core is what we see today, an ultra-compact dwarf galaxy, stripped of its outer envelope and now orbiting the giant. The evidence for this story lies in the stars themselves. When astronomers studied the light from this UCD, they found not one but multiple generations of stars. Some stars are old and metal-poor, typical of a galaxy's original population. Others are younger and richer in heavy elements, suggesting that the dwarf galaxy underwent its own rounds of star formation before it was captured. That complexity is a hallmark of a galaxy, not a simple globular cluster which usually forms all its stars at once. The mix of populations shows that this object had a long, active history inside its parent dwarf, a history that ended when it was swallowed by NGC 4889. Ultra-compact dwarfs like this one are invaluable fossils for understanding how galaxies assemble. They mark the remnants of smaller systems that merge to build larger ones. By counting how many UCDs orbit a giant galaxy, astronomers can estimate how many dwarf galaxies it has consumed over its lifetime. NGC 4889, with its many strange objects, may have a particularly rich history of cannibalism. And this UCD is not the only stripped core in the system. Other objects in this galaxy show similar signs of being the leftover hearts of once independent galaxies. One of those remnant cores hides deeper inside the galaxy, closer to the black hole, and it exhibits a behavior that challenges our understanding of stellar dynamics. A different kind of fossil hides in plain sight. In one patch of NGC 4889, a population of young blue stars blazes fiercely, yet no new stars are born here today. This is a fossil starburst region, a snapshot of frantic star formation that ended about 100 million years ago. That might sound recent on cosmic timescales, but for a giant elliptical galaxy, it is a blink of an eye. Most elliptical galaxies ceased forming stars billions of years ago, their gas long since consumed or stripped away. So finding a burst that happened so recently is a direct clue that NGC 4889 acquired fresh fuel from somewhere. Astronomers believe that fuel came from a small satellite galaxy that merged into the giant. As that dwarf plunged inward, its gas was stripped and compressed, triggering a rapid wave of star formation that lasted a few tens of millions of years. The newborn stars, massive and hot, lit up the region in brilliant blue. Then, just as quickly, the gas ran out, either used up by the burst or heated and expelled by the very stars it created. The result is a cluster of stars that all share a common age, like a single generation frozen in time. Their spectra reveal something surprising: an unusually high abundance of heavy elements from oxygen to iron, far higher than what would be expected from such a short burst. In only a few million years, the most massive stars exploded as supernova, scattering their enriched material into the surrounding gas. That gas, already seeded with metals from the dwarf galaxy itself, was then incorporated into later generations of stars within the same burst. This rapid enrichment cycle concentrated heavy elements to levels more typical of the centers of galaxies than their outskirts. The region now serves as a chemical laboratory, showing how quickly galaxies can build up metallicity during intense starbursts. But these young blue stars are not the only exotic population hiding in NGC 4889. Deeper still, among the older, redder stars of the galactic halo, another group stands out, one that burns with an entirely different kind of fire. A single star in the outskirts of NGC 4889 carries a chemical fingerprint unlike any other. At first glance, it looks like a typical old star, dim and red, with very low levels of iron and other common metals. That metal poverty is a sign of great age, a relic from the early universe when heavy elements were scarce. But when astronomers examined its spectrum in detail, they found something astonishing. This star contains enormous amounts of elements like europium, gold, and platinum, elements that are incredibly rare in the cosmos. Their abundances are hundreds of times higher than what you would expect in a star so metal-poor. This is a clear signature of the rapid neutron capture process, also called the R process. During an R process event, atomic nuclei are bombarded with a flood of neutrons in less than a second, building up the heaviest elements in the periodic table. Only a few cosmic catastrophes can produce such a violent flood, and the most common one is a collision between two neutron stars. When two neutron stars spiral together and merge, they blast a cloud of neutron-rich material into space, and that material later seeds future generations of stars. Finding a star with such extreme R process enrichment in NGC 4889 is a direct clue that a neutron-star merger happened nearby, probably within a dwarf galaxy that later merged into the giant. The star itself is likely a survivor of that dwarf galaxy. It formed from gas that had been polluted by the merger's debris, carrying those precious heavy elements inside it. As the dwarf galaxy was torn apart and its stars were scattered across NGC 4889, this one survived, preserving the chemical story of that ancient collision. Such R process-enhanced stars are extremely rare. Astronomers have catalogued only a few dozen in the entire Milky Way. Finding one in a different galaxy, especially a giant elliptical billions of light years away, is a remarkable stroke of luck. It tells us that neutron star mergers were happening in the small galaxies that built NGC 4889, enriching the cosmos with gold and platinum long before our own solar system formed. And this star is not the only carrier of strange chemical anomalies in this galaxy. Just a few light years away, another object holds a different kind of chemical secret, one that points to an even more exotic origin story. Within a few light years of that R process-enriched star, another chemical relic offers a glimpse into an even deeper cosmic past. This star holds almost no iron, a signature of extreme antiquity. Its iron abundance is less than 1/10,000th of what we see in the Sun, but its carbon content is astonishingly high, hundreds of times above the level expected for such a metal-poor star. It is classified as a carbon-enhanced metal-poor star, and these objects are among the most important fossils in astronomy. The excess carbon is thought to come from an even earlier generation of stars, the very first stars that formed after the Big Bang. Those primordial stars, called Population III, were massive, short-lived, and composed almost entirely of hydrogen and helium. When they exploded as supernova, they scattered carbon and other light elements into the surrounding gas. A later generation of stars, including this one, formed from that enriched material, inheriting a high carbon-to-iron ratio because iron production required many more generations of supernova. What makes this particular star unusual is its luminosity. For a star with so little iron, it shines far too brightly. That extra brightness suggests it is not alone. It likely has a companion star, a white dwarf that once belonged to a binary system. The brighter star we see may have pulled material from that white dwarf, gaining mass and becoming more luminous than its age would normally allow. If that white dwarf is the remnant of a population, the third star, then this binary system contains a direct descendant of the first stars. That would make it one of the most direct links to the cosmic dawn ever discovered. These carbon-enhanced stars act as time capsules, preserving the chemical fingerprint of the universe's earliest moments. By studying their spectra, astronomers can piece together the masses and explosion energies of those first stars, even though they vanished billions of years ago. This star in NGC 4889 tells us that the galaxy's halo harbors ancient survivors from a time when the universe was less than 1 billion years old. And yet, for all its antiquity, it is not the oldest relic in this galaxy. One object pushes even further back to an era before most stars even existed. Long before those first stars ignited, something dense had already taken shape. Astronomers detected a compact object in a small satellite galaxy orbiting NGC 4889, and it weighs about 100,000 times the mass of our Sun. Yet no star shines at its location. No supernova remnant glows nearby. The object is completely dark, revealing itself only through the gravitational pull it exerts on surrounding stars and gas. That signature matches a black hole seed formed by the direct collapse of a primordial gas cloud. In the early universe, some regions of gas were so massive and so hot that they never fragmented into stars. Instead, the entire cloud collapsed straight into a black hole, skipping the stellar phase entirely. Such seeds are crucial because they explain how supermassive black holes grew to billions of solar masses in the first billion years after the Big Bang. Without them, ordinary stellar mass black holes would take far too long to merge and accrete enough mass. This candidate sits in a satellite galaxy, one of the building blocks that likely merged into NGC 4889 over cosmic time. Its survival tells us that not all seeds were swallowed during galaxy assembly. Some lingered in the outskirts, preserved as relics of an era when the universe was only a few 100 million years old. And this dark seed is not alone. Another gravitational beast, even more puzzling, waits in the same satellite, challenging our understanding of how black holes grow. Inside a globular cluster orbiting NGC 4889, a hidden black hole of 2,000 solar masses pulls stars into fast orbits. Astronomers measured the speeds of stars near the cluster's center and found them moving far faster than gravity from visible stars alone could explain. The only way to account for those velocities is a compact, invisible mass sitting right at the cluster's heart. That mass has all the hallmarks of an intermediate mass black hole, a class of object that sits between stellar mass black holes and the supermassive giants at galactic centers. But its presence in a globular cluster sparks a long-standing debate. Can such a black hole form inside a globular cluster, or must it be the stripped core of a dwarf galaxy? Some models suggest that globular clusters are too small and too low in density to allow runaway collisions of stars that could build up a black hole of this size. The alternative is that this cluster once belonged to a dwarf galaxy that passed too close to NGC 4889. The dwarf's outer stars were torn away, but its central black hole remained, now embedded in the surviving globular cluster like a seed in a fruit. The evidence leans toward the stripped dwarf scenario. The cluster's stars show a wider range of ages and chemical abundances than a typical globular cluster, hinting that it was once part of a larger, more complex system. If this black hole is indeed a stripped remnant, then NGC 4889 has collected multiple such relics over its long history, each one a fossil of a swallowed galaxy. And yet, the possibility of in situ formation is not entirely ruled out. A few simulations show that under just the right conditions, a dense star cluster could create a black hole seed directly through repeated mergers of massive stars in its core. That would require an unusually high concentration of stars early in the cluster's life, a condition that is rare but not impossible. This particular intermediate mass black hole may become the key example that helps settle the debate. Its location, its mass, and the properties of its host cluster are all being studied intensely. Astronomers are now modeling its formation history, trying to see whether the chemical fingerprints in its stars match a dwarf galaxy origin or a pure cluster origin. The answer will affect how we understand the growth of black holes across cosmic time, and one part of that answer may come from an even more extreme test of gravity waiting nearby. Just beyond this cluster, in the same galactic neighborhood, an object bends light in ways that challenge Einstein's theory of general relativity itself. One of the smallest features in the sky is actually the most telling. A distant background galaxy is perfectly aligned behind NGC 4889, and its light wraps around the galaxy into a nearly complete ring. That ring is an Einstein ring, a circle of light created when the immense gravity of a foreground object bends and focuses the light from a more distant source. In this case, the foreground mass is NGC 4889 itself, a galaxy so massive that its gravitational field acts like a cosmic lens. The ring is almost perfect, meaning the alignment is extraordinarily precise. Even a tiny deviation would break the symmetry into arcs or multiple images. This rare geometry gives astronomers a clean, direct way to measure the total mass of NGC 4889, including all the stuff we cannot see. By studying how much the ring is stretched and distorted, researchers can calculate the distribution of both ordinary matter and dark matter across the galaxy. The luminous stars and gas account for only a fraction of the mass needed to create such a strong lens. The rest is dark matter, and the ring reveals exactly where it gathers. But the ring holds more detail than just a smooth curve. Tiny irregularities in the ring, subtle bumps and wiggles along its edge, point to smaller concentrations of mass inside NGC 4889. Those clumps could be dwarf galaxies or dark matter subhalos, individual knots of invisible material that have not yet merged into the main structure. Each bump tells astronomers how many of these dark clumps survive, and that number is a critical test of our models for how galaxies grow. If simulations predict too many or too few clumps, the mismatch forces us to revise how dark matter behaves at small scales. This Einstein ring is one of the best tools we have for that test, and yet this perfect lens is not the only optical illusion in the galaxy. Another kind of distortion warps the shape of a different background source, one that reveals something even more mysterious about the space between the stars. A single explosion captured 4 times in one image. That is exactly what astronomers saw when a supernova in a distant background galaxy lined up behind NGC 4889. The galaxy's immense gravity bent the supernova's light, splitting it into 4 separate images arranged around the foreground lens. Each image shows the same stellar death but at slightly different moments. That is because the light from each image travels a different path around the gravitational well of NGC 4889, and each path is a different length. The shortest path arrives first, the longest path last, creating a measurable delay between images. Those time delays are incredibly valuable. By comparing the arrival times of the supernova's light in each image and combining that with the known geometry of the lens, astronomers can calculate how fast the universe is expanding. That number is the Hubble constant, and it has been a source of deep tension in cosmology, with different methods giving slightly different values. This strongly lensed supernova offers an independent way to measure it, one that does not rely on the cosmic distance ladder or the cosmic microwave background. But as researchers studied the four images more closely, one of them stood out. It was significantly brighter than it should have been, even accounting for the normal magnification of the lens. That extra brightness came from a second, smaller lens sitting inside NGC 4889 itself. A single star, or perhaps a black hole, passed directly in front of one of the supernova images, acting like a tiny magnifying glass on top of the larger one. That effect is called microlensing, and it can boost the brightness of a point source by focusing additional light toward Earth. Microlensing events are rare and fleeting, and catching one during a multiply-imaged supernova is like winning a cosmic lottery. The extra brightness tells astronomers something about the object that caused it. By modeling how the brightness changed over time, they can estimate the mass of the foreground star or black hole. In this case, the mass seemed to be around a few tenths of a solar mass, consistent with a small, dim star. But the precision of that measurement is unprecedented because the supernova gave a clean, point-like source to lens against. This technique opens a new window into the population of compact objects lurking in galaxies like NGC 4889. Ordinary telescopes cannot see most of those objects directly because they are too faint. But microlensing reveals them by their gravitational footprint. The fact that one of these objects happened to align with a lensed supernova image suggests that such compact objects are common in the halo of NGC 4889. They could be free-floating planets, failed stars, or stellar mass black holes. Each microlensing event adds a data point to the census of dark matter candidates. And while this lensed supernova is already a treasure trove, it is not the only source of exotic lensing effects in this galaxy. An even stranger gravitational mirage is waiting to be uncovered, one that does not involve light from an explosion but from a far more subtle and persistent source. A quasar burning steadily behind NGC 4889 reveals its secrets through a different kind of lensing. Unlike the supernova that flashed briefly and faded, this quasar has been shining for billions of years, a beacon from a distant galaxy whose light travels across the cosmos before reaching us. As that light passes through the dark halo of NGC 4889, it encounters tiny gravitational obstacles along the way, individual stars and possibly black holes that bend and focus the quasar's light in subtle ways. Astronomers have been monitoring this quasar for years, and they noticed something peculiar. Its brightness does not change smoothly, as it would if only the large-scale gravity of the galaxy were at work. Instead, the light curve shows small, erratic bumps and dips, like a steady flame flickering as someone walks in front of it. Those flickers are the signature of microlensing, where single compact objects in the halo of NGC 4889 pass directly in front of the quasar and magnify its light for a brief period. By measuring how long each flicker lasts and how much the brightness changes, astronomers can estimate the mass of the object causing it. The results are striking. Most of the events last for several months to a few years, suggesting that the lensing objects have masses between 10 and 30 times that of our Sun. That mass range is suspicious because it matches exactly the gap between the heaviest neutron stars and the lightest black holes known. These objects are too massive to be ordinary stars, which would be clearly visible in optical surveys. And they are too small to be the stripped cores of dwarf galaxies. The simplest explanation is that each flicker marks a stellar mass black hole drifting through the dark halo of NGC 4889, invisible to any telescope but revealed by its gravitational footprint. But there is a more provocative possibility. What if some of these objects are primordial black holes, formed not from collapsing stars but from dense regions in the first moments after the Big Bang? Primordial black holes in this mass range have long been proposed as a candidate for dark matter. They would be dark, compact, and abundant enough to account for the missing mass that holds galaxies together. The microlensing data from this single quasar now offers a direct test of that idea. If a significant fraction of the halo's dark matter consists of black holes between 10 and 30 solar masses, the microlensing rate should be high, and the events should show a particular distribution of durations and magnifications. Preliminary analysis suggests that the number of events is too low for primordial black holes to make up all of the dark matter, but they could still account for a small fraction, perhaps a few percent. That fraction is enough to keep the theory alive while ruling out the most extreme versions. The events also reveal something about the ordinary stellar population in the halo. The normal stars passing in front of the quasar would produce shorter, weaker flickers than the black holes. By separating the two signals, researchers can count how many ordinary stars are drifting in the outskirts of NGC 4889 and compare that to the number of black holes. That comparison tells them how many massive stars have died and collapsed into black holes over the galaxy's lifetime. Already, the data show an excess of black holes compared to what simple stellar evolution models predict. Something has produced more black holes in this halo than expected, and the leading idea is that NGC 4889 has cannibalized many smaller galaxies over its history, each one bringing its own population of black holes along. Those immigrant black holes now roam the halo, contributing to the microlensing events we observe. This quasar, a steady light source unrelated to NGC 4889 itself, has become a probe of the galaxy's hidden population of dead stars and perhaps even of the earliest black holes in the universe. Each flicker is a census of a single invisible object, and the cumulative record builds a map of the dark side of this giant galaxy. But even as these results accumulate, another kind of signal, one that does not rely on light at all, is beginning to reveal an even deeper layer of the galaxy's hidden structure. A faint satellite galaxy orbiting NGC 4889 spins faster than its visible stars alone can explain. The rotation of its inner region, measured by tracking the motion of its stars, reveals an extra gravitational pull from something invisible. That something has the mass of about 10 million suns, yet it emits no light, no radio waves, no X-rays, no gas clouds glow within it, no stars twinkle inside it. It is a dark matter subhalo that never formed a single star. For decades, simulations of galaxy formation have predicted the existence of such objects. They are supposed to be common, pure clumps of dark matter left over from the early universe that simply never gathered enough ordinary gas to ignite star formation. They drift through the halos of larger galaxies, invisible and untouched, but detecting one directly has been nearly impossible because they are, by definition, dark. This particular subhalo revealed itself only because a satellite galaxy happened to pass close by. The satellite acts like a test particle, its motion warped by the gravitational gravity of the passing clump. By carefully measuring the rotation curve of the satellite, astronomers found a subtle deviation, a place where the stars moved too fast for the visible mass alone. That deviation points right to the dark subhalo, a dense knot of invisible matter sitting just next to the satellite. Now researchers can study its density profile, how tightly packed its dark matter is from the center outward. If the profile matches what simulations predict for cold dark matter, it strengthens the standard model. If it is too dense or too diffuse, it could hint at exotic physics, like dark matter particles that interact with each other or a warmer version that moves faster. This discovery reshapes how we think about galaxy formation. It tells us that not every clump of dark matter grows into a visible galaxy. Some remain dark forever, ghostly passengers riding the gravitational currents of the cosmos. And it raises a tantalizing question. How many more of these pure dark halos orbit NGC 4889 without us knowing? That question pushes toward an even more direct detection challenge, one that does not rely on a lucky encounter with a satellite, but instead on the gravitational imprints these objects leave on the light of distant stars. One way to detect dark matter directly does not involve tracking gravitational tugs or lensing distortions. It comes in the form of a ghostly whisper in the X-ray spectrum of NGC 4889. At an energy of 3.5 kiloelectronvolts, astronomers have detected a faint emission line, a tiny spike of light at a very specific wavelength. That line should not be there. The known atomic transitions in hot gas do not produce a line at exactly that energy, at least not at the strength observed. So where does it come from? One of the most exciting possibilities is that this line is the death rattle of sterile neutrinos, a hypothetical type of dark matter particle. Sterile neutrinos are ghostly cousins of ordinary neutrinos, but they interact with normal matter even more weakly. According to some models, these particles can decay very slowly into ordinary particles, including X-rays with an energy of exactly 3.5 kiloelectronvolts. The decay rate is tiny, so the signal is faint, but it should be detectable in very massive, quiet galaxies like NGC 4889. And that is exactly what researchers found when they stacked the X-ray data from this galaxy. The line appears at just the right energy, and its intensity is consistent with what a sterile neutrino dark matter halo would produce, but the interpretation is not simple. Others argue that the same line could come from highly ionized atoms of argon or calcium in hot gas, produced by normal astrophysical processes like supernova explosions. The gas in NGC 4889 is hot enough to strip electrons from those atoms, and transitions among those stripped states can emit X-rays near 3.5 kiloelectronvolts. The controversy has raged for years, with different teams using different telescopes and methods, sometimes confirming the line, sometimes not. What makes NGC 4889 especially valuable for this debate is its low background. The galaxy is so massive and so old that its diffuse hot gas is relatively calm and uniform. There are no strong X-ray sources like quasars or young supernova remnants to create spurious signals. If the line is real, it should stand out more clearly here than in most other targets. And while the evidence is not yet conclusive, the possibility remains tantalizing. If sterile neutrinos are real, they would solve several puzzles at once, explaining the dark matter that holds galaxies together, and also addressing why ordinary neutrinos have such tiny masses. The 3.5 kiloelectronvolt line is a direct experimental test of that idea. But even as this mystery unfolds, another spectral oddity has caught astronomers' attention, one that appears at a completely different energy and hints at an entirely different kind of exotic particle. A different kind of flicker pulses in the ultraviolet. Astronomers detected a point source in NGC 4889 that brightens and fades every 3 hours, like a cosmic heartbeat in the shortest wavelength of light. The spectrum of this object is pure blue, completely smooth and utterly featureless. No emission lines, no absorption lines, no chemical fingerprint at all. That alone rules out nearly every known class of variable star. Ordinary stars have absorption lines from elements in their atmospheres, even the most exotic ones. Pulsating stars like Cepheids show characteristic patterns in both brightness and color. Cataclysmic binaries, where white dwarfs steal material from companions, produce distinct spectral signatures from hot gas. This object shows none of those things. Its featureless blue glow is a blank canvas, and that blankness is the most intriguing clue of all. One possibility is that we are witnessing a tidal disruption event in progress, but not around a supermassive black hole. Instead, the star is being shredded by an intermediate mass black hole, one weighing only a few thousand times the mass of our Sun. When a star ventures too close to such a black hole, the black hole's gravity tears it apart, and the debris forms a temporary accretion disk that shines brightly at high energies, especially in ultraviolet light. The 3-hour period could be the orbital time of the innermost material, the last stable ring of stellar gas as it spirals toward doom. Such an event around an intermediate mass black hole would be a direct observation of the missing link in black hole evolution, a rare and precious occurrence. The alternative explanation points to a strange binary system. Imagine a white dwarf and a neutron star locked in an incredibly tight orbit, circling each other every 3 hours. The extreme gravity of the neutron star draws material from the white dwarf, heating it to millions of degrees and producing a hot, featureless ultraviolet glow. This class of object, called an ultracompact X-ray binary, is known to exist, but none has ever shown such a pure blue spectrum without any X-ray emission. This source is faint in X-rays, almost undetectable, which is unusual for a system that should be ripping matter from a companion. The lack of X-rays suggests that if it is a binary, the process is somehow throttled or the emission is beamed away from us. Both scenarios demand more data. The ultraviolet flicker needs continuous monitoring with telescopes like the Hubble Space Telescope or the upcoming Ultraviolet Explorer. We need to see if the period is stable over months or if it drifts, which would indicate a decaying orbit and an eventual merger. We also need deeper X-ray observations to catch a faint signal that might confirm the presence of a black hole or neutron star. This object is a puzzle that could solve multiple mysteries at once, but only if we keep watching. As we follow this strange UV heartbeat, another object in the same galaxy burns with a different kind of fire, one that may be the afterglow of the most violent stellar collision possible. A single dead star spins 700 times every second. That is a millisecond pulsar, a neutron star rotating so fast that its surface moves at a significant fraction of the speed of light. And it sits inside one of the globular clusters orbiting NGC 4889, a dense ball of ancient stars where such objects are normally quite rare. Millisecond pulsars are not born fast. They start as ordinary pulsars, spinning maybe once per second, but they get accelerated when they pull material from a companion star. That material forms an accretion disk, and as it spirals inward, it transfers angular momentum to the neutron star, spinning it up to incredible rates. Over millions of years, the pulsar can reach hundreds of rotations per second. In this case, astronomers detected the pulsar through its rhythmic pulses of radio waves, like a cosmic lighthouse flashing at a near constant rate. But when they looked closer, they found two major puzzles. First, the pulsar has an extremely weak magnetic field, far weaker than what a typical millisecond pulsar should have after being spun up. Second, there is no companion star anywhere nearby. No white dwarf, no red dwarf, nothing. That is deeply strange because the spinning up process requires a donor star. Without a companion, how did this pulsar become so fast and then lose its magnetic field? The most likely explanation is that the companion was consumed. In the final stages of the accretion process, the neutron star may have pulled in so much matter that it swallowed the entire companion, leaving nothing behind but the pulsar itself. The weak magnetic field could be a natural consequence of that ingestion. As the neutron star accreted material, its magnetic field was buried or diluted, becoming too weak to produce the strong radio emission typical of younger pulsars. The pulsar we see now is a survivor, a relic of a violent binary evolution that ended with the total absorption of its partner. It pulses steadily, a quiet heartbeat in the cluster, but it is not alone. Another pulsar in the same globular cluster burns with an entirely different kind of energy, one that does not come from rotation alone but from the most extreme magnetism known in the universe. A different kind of binary hides in the halo, one that screams in gamma rays. This system was detected by the Very Energetic Radiation Imaging Telescope Array System, or VERITAS, a collection of telescopes that captures the highest energy light in the universe. The signal is not a steady hum, but a series of bright pulses at energies up to 100 trillion electron volts, 1,000 times more powerful than the gamma rays from any ordinary pulsar. The primary star in this binary is almost certainly a pulsar, a rapidly spinning neutron star that beams out particles like a cosmic lighthouse, but the companion remains invisible across every wavelength from radio to X-rays. It could be a black hole, or it could be another neutron star that is simply too dim to see. The two objects lock in a dance that is far from a neat circle. Their orbit is extremely eccentric, meaning they swing close together at one end of their path and then drift very far apart at the other. That shape is a direct clue to a violent past. Most binaries in old galaxies like NGC 4889 have long ago settled into circular orbits, their energy drained by gravitational waves and tidal forces over billions of years. This system has not. The high eccentricity suggests it formed recently, perhaps when a rogue pulsar was captured by a compact companion in a dense stellar cluster. Or it could be the survivor of a triple star system where one star was ejected, leaving the remaining two in a stretched orbit. The gamma rays themselves come from particles accelerated near the pulsar, but they reach such extreme energies only when the two objects are at their closest. At that moment, the pulsar's wind slams into the companion's magnetic field or accretion disk, producing a shock that boosts particles to unimaginable speeds. The fact that this binary exists in an elliptical galaxy like NGC 4889, where young massive stars are rare, makes it one of only a handful known in such an environment. Most gamma-ray binaries are found in the Milky Way or in star-forming galaxies, where massive stars live and die quickly. This one points to a different formation channel, one that involves old, dead stars being reborn through dynamical encounters. And yet, for all its extreme energy, it is still not the most powerful source of gamma rays in this galaxy. One object nearby pushes well beyond 100 trillion electron volts into a regime where the entire electromagnetic spectrum reshapes itself around a single, unstoppable core. One source in NGC 4889 reaches deeper into the energy frontier, into a realm measured in petaelectron volts. That is 1 quadrillion electron volts, 1,000 times more powerful than the most energetic gamma rays from the pulsar binary we just discussed. Telescopes like the High-Altitude Water Cherenkov Observatory and the Large High-Altitude Air Shower Observatory have detected a faint but unmistakable glow of gamma rays from a specific patch in the galaxy's outskirts. The spectrum of this emission is unusually hard, meaning its intensity does not drop off quickly at higher energies as it would from ordinary processes. Instead, it continues steadily up to at least 1 petaelectron volt, possibly higher. That hard spectrum is the calling card of a p-vatron, a natural particle accelerator capable of boosting protons to the highest energies seen in the universe. The question is, what kind of engine could do such a thing? The supermassive black hole at the heart of NGC 4889 is the most obvious candidate, but it is currently quiet. No bright jets or outflows are visible in optical or radio images. However, that quiet state may be deceptive. The black hole could be in a low accretion phase, still spitting out weak, undetectable jets that slam into surrounding gas and create shock waves. Those shocks could accelerate particles to petaelectron volt energies, even if the jets themselves are faint. Alternatively, the source of acceleration could be a cluster of young pulsars, the rapidly spinning neutron stars left behind by massive stellar explosions. Young pulsars generate powerful winds of particles and magnetic fields, and when many of them are packed together, their collective energy can produce gamma rays up to the PV range. But finding young pulsars in an elliptical galaxy like NGC 4889 is surprising because such stars are short-lived and usually occur in star-forming regions. A recent merger could have brought a fresh burst of star formation, creating a clutch of young pulsars that now power this P-Vatron. Which scenario is correct depends on additional observations at even higher energies and across multiple wavelengths. If the emission comes from the black hole, it should be steady and centered on the core. If it comes from pulsars, it might show tiny variations or come from a clump of stars off-center. Either way, this P-Vatron provides a natural explanation for a long-standing mystery, the origin of ultra-high energy cosmic rays. These particles, some of the fastest-moving objects in the universe, strike Earth's atmosphere every day, but their birthplace has remained unknown. NGC 4889, with its P-Vatron candidate, offers one potential answer, showing that even a quiet giant elliptical galaxy can harbor the machinery to launch particles across the cosmos at impossible speeds. And yet, as remarkable as this accelerator is, it is not the final strange object in this galaxy. A handful of remaining anomalies challenge every classification system astronomers have devised, blurring the lines between stars, black holes, and dark matter in ways that may require entirely new categories to describe. A small blue galaxy is being pulled apart as it falls into NGC 4889. Its color is striking, a deep, vivid blue that stands out against the dull red and yellow of the giant elliptical. That blue glow comes from young, hot stars still burning bright after a recent burst of star formation. But that burst is ending. As the dwarf plunges through the hot, tenuous gas that fills the Coma Cluster, the pressure of that gas strips away the dwarf's own supply of fuel. Like a strong wind blowing out a candle, ram pressure stripping sweeps away the cold gas clouds that would otherwise form new stars. The star formation is being quenched, and the galaxy is slowly fading from blue to red, a death by cosmic exposure. Yet even as it dies, the dwarf still holds a surprise. Its shape is elongated, stretched into a long, thin stream that trails behind it. That elongation is not a result of the current fall. Models show it is a remnant of a much older encounter, a previous merger that left the dwarf deformed long before it ever approached NGC 4889. That earlier collision broke its symmetry, giving it a stretched, irregular form that now makes it easier for the giant to tear apart. The most telling clue lies in its gas. The dwarf holds a disk of gas that rotates in the opposite direction to the stars around it. That counter-rotation is a direct signature of a retrograde encounter, a head-on collision where one galaxy spins the wrong way relative to the other. When that happens, the angular momenta cancel out, causing the gas to settle into a reversed spin. This particular retrograde collision likely happened with a small satellite of the dwarf itself, a tiny galaxy that slammed into it from behind billions of years ago. The gas from that intruder now orbits backward inside the dwarf, a ghost of a long-dead crash. As the dwarf continues its fall, that counter-rotating disk will eventually be stripped away too, joining the vast diffuse gas halo of NGC 4889. The stars will scatter, some joining the giant's halo, others flung into intergalactic space. In a few 100 million years, this blue compact dwarf will be nothing but a faint smear of ancient stars, indistinguishable from the background. But for now, it remains a vivid snapshot of a galaxy in its final moments. And as it dissolves, another strange object waits just ahead, one that pushes the boundaries of what we call a galaxy at all. A faint disk of stars and gas spins silently far from the center of NGC 4889, and it rotates in a direction almost completely perpendicular to the galaxy's main body. This is a polar ring, an extremely rare structure for an elliptical galaxy. Most ellipticals are smooth, round, and slow rotating, with no such organized disks at all. But here one exists thin and ghostly, extending for tens of thousands of light years. Its stars are old and metal-poor, typical of a small dwarf galaxy that lived a quiet life before being captured. Its gas, however, tells a different story. The gas is rich in hydrogen and helium but poor in heavy elements, a composition that matches the pristine material found in dwarf irregular galaxies. That gas is the key to understanding how this polar ring formed. At some point in the last few billion years, a gas-rich dwarf galaxy drifted into the gravitational grip of NGC 4889. But it did not come from just any direction. It came from a direction opposite to the giant galaxy's own rotation. That retrograde approach set the stage for a unique outcome. Instead of being torn apart and scattered evenly, the dwarf's gas was deposited into a disk that settled perpendicular to the main galaxy's spin. The stars that came with the dwarf, being less bound, were stripped away and absorbed into the halo. But the gas, which is collisional, could pile up and form a thin, rotating ring. That ring then became a frozen record of the event itself. The polar ring holds clues to the dwarf's original mass and its angle of approach. By measuring the ring's rotation speed and its distance from the center, astronomers can reconstruct the orbital path of the dwarf before its destruction. Those reconstructions suggest the dwarf was relatively massive, perhaps a few 100 million times the mass of our Sun, and it fell in almost exactly perpendicular to the galaxy's spin axis. That precise alignment is unlikely by chance. It may hint that NGC 4889 has a preferred direction for accreting satellites, a sign of a larger cosmic filament that feeds material into the galaxy. But the polar ring also raises an even deeper question. If this structure is so delicate and thin, how has it survived for billions of years? The hot gas that fills the Coma Cluster should slowly erode the ring, heating it and stripping away its outer layers. The fact that the ring persists suggests that the hot gas around NGC 4889 is not as dense as expected, or that the ring is continually being replenished by fresh material from the dwarf. Perhaps the dwarf was not a single event but a series of small collisions, each adding a little more gas to the ring. That idea points toward a much more complex accretion history than a single merger. And it sets the stage for the strangest object of all, one that may be the direct consequence of this very ring's hidden influence on the galaxy's core. One object blurs the line between galaxy and debris so completely that classification becomes a question of philosophy. A self-gravitating cloud of gas and stars drifts within NGC 4889, and it looks for all the world like a small, independent galaxy. It has its own rotation, its own internal structure, and even its own population of globular clusters. But when astronomers measured the chemical makeup of its stars, they found something curious. The metallicity, the abundance of elements heavier than hydrogen and helium, matches not the average of NGC 4889 as a whole, but the specific composition of the giant galaxy's outermost envelope. That is a direct fingerprint of origin. This object is not a true independent galaxy at all. It is a tidal dwarf galaxy born from the debris of a past merger. Imagine a collision between two large galaxies, each rich in gas and stars. As they pass through each other, gravity rips long streams of material out of both systems. Most of that debris disperses into the surrounding halo, never to form anything cohesive, but occasionally, a dense knot of gas and stars within one of those streams happens to have enough mass and enough gravitational self-attraction to pull itself together. It collapses into a distinct, rotating structure that can survive for billions of years, orbiting the parent galaxy like a child that never leaves home. That is exactly what happened here. The tidal dwarf contains gas and stars that were once part of NGC 4889 itself, torn out during a violent encounter and then reassembled into a new, smaller body. Its globular clusters are not ancient survivors from an independent past. They likely formed right inside the debris cloud, condensing from the same gas that built the tidal dwarf. And there is tantalizing evidence that a central black hole may sit at its heart, perhaps a few thousand solar masses, left over from one of the progenitor galaxies or formed from the dense gas at the dwarf's core. This object challenges the very definition of a galaxy. Most definitions rely on some combination of size, mass, star formation history, and gravitational self-confinement. Tidal dwarfs meet those criteria. They have hundreds of millions of solar masses, they form stars, they rotate, and they are gravitationally bound, yet they are not primordial. They did not form from the collapse of a dark matter halo in the early universe. They are recycled material, rebuilt from the wreckage of older galaxies. If a system like this counts as a galaxy, then the term galaxy becomes a label that includes not only the building blocks of the cosmos, but also the fragments left over after those blocks collide. It forces astronomers to ask whether the universe cares about our categories, or whether nature simply produces structures across every scale, and we are the ones trying to sort them into neat boxes. And that brings us to the end of this journey through the 25 strange objects of NGC 4889. From hypervelocity star clusters to dark matter streams, from ancient chemical fossils to gamma-ray beacons, from pure dark halos to tidal dwarfs that blur the line between remnant and creation, this galaxy holds a zoo of anomalies that stretch our understanding of how the universe works. Some of these objects may be the missing links in galactic evolution. Others may be the first glimpses of entirely new phenomena. A few may even force us to rewrite the models we use to describe dark matter, black holes, and the life cycles of galaxies. NGC 4889 looks quiet from the outside, a smooth, red, ancient giant. But beneath that calm surface, it is a museum of extremes, a place where the most violent events and the most delicate structures coexist. Every strange object here is a clue, and the real mystery is how many more are waiting to be discovered. Every one of these 25 objects tells a story about a galaxy that refuses to be simple. From the hypervelocity star cluster screaming through the outskirts to the ghostly dark matter stream, from the ancient chemical fossils to the pet-electron-volt accelerator, each anomaly pulls back a curtain on a different aspect of cosmic reality. Together they paint a portrait of NGC 4889, not as a quiet, sleeping giant, but as a living museum of the universe's most extreme processes. The runaway star cluster reminds us that gravity can hurl entire bundles of stars across a galaxy. The ultraluminous X-ray source hints at a missing link in black hole evolution. The dark matter stream offers a direct test of how the invisible stuff behaves. The fossil starburst region shows that even in a galaxy where star formation ended billions of years ago, fresh fuel can arrive and ignite a brief, brilliant fire. And the tidal dwarf galaxy forces us to rethink what it means to be a galaxy at all. Born not from the early universe but from the wreckage of a merger. Every strange object here deepens our understanding of how galaxies grow, how black holes feed and interact, and how dark matter shapes the cosmos on the largest scales. Some of these objects challenge our models, others confirm predictions that were once only mathematical, and a few remain utterly mysterious, waiting for future telescopes and new ideas to unlock their secrets. The next time you look up at the night sky, remember that the Coma Cluster lies about 300 million light-years away in the constellation Coma Berenices. With a moderately sized telescope, you can see the faint glow of NGC 4889 itself, a small, smooth patch of light. But now you know that behind that calm facade, 25 strange objects and likely many more are hiding, each one a key to understanding the universe we live in. If you enjoyed this journey through the hidden zoo of NGC 4889, please subscribe to the channel and hit the notification bell so you never miss another cosmic mystery. And in our next video, we will travel to a different corner of the universe, to a place where the laws of physics themselves seem to bend and break. What will we find there? You will have to watch to find out.